our day-to-day activities irrespective of what we do. You would definitely have observed that while cooking food, measured quantities of ingredients are cooked for a measured amount of time. When you go to buy, this is possible by making them run a known distance, say from one end of a playground to the other. Measurement in science and technology. Measurement is a basic skill which forms an essential part of our day-to-day activities irrespective of what we do. You would definitely have observed that while cooking food, measured quantities of ingredients are cooked for a measured amount of time. When you go to buy fruits and vegetables, you take them in measured amounts. You can identify which one of your friends runs fastest. This is possible by making them run a known distance, say from one end of a playground to the other, and noting who is first to reach the destination. In other words, you measure the time. Can you tell by the above measurement how fast does your friend run? For this, you need to precisely measure the distance. Science and technology helps us in making precise measurements for our daily life activities such as stitching, cooking, sports, shopping, traveling, etc. In this lesson, we would like to seek answers to several questions. What is the measurement and why do we need it? How do we measure? How do we quantify a measurement so that it is understood by everyone in the same sense? What is the currently accepted international system of units? We would also learn about commonly used tools for measurement of the physical quantities like length, mass, time, area, and volume. Objectives. After completing this lesson, you will be able to: number 2, define measurement and explain the need for measurement. Number 2, give examples of the parts of human body that may be used to measure length of an object and state the limitations of such measurements. Number 2, describe the Indian and various other measurement systems used in ancient times. Number 2, explain of a common system of units. Number 2, define and differentiate base and derived SI units. Measurement is science. Notes. Number 2, derive the SI unit of a physical quantity. Number 2, explain the need of SI prefixes. Number 2, use SI prefixes for the units n. Number 2, correctly write the SI units using the rules for writing the same. 1.1 What is a measurement? Suppose you are asked to measure the length of a playground, what would you do? Maybe you would walk from one end of the field to the other and count the number of steps. The other possibility is that you may arrange for a measuring tape or some scale, say a meter scale. Then again go from one end and count how many times the meter scale was used to reach the other end. Let us take another example. Suppose you need to weigh a carton full of books, you would use a weighing scale and see how many kilogram weights you need to correctly weigh the carton again. A kind of counting. Thus we may define measurement to be a counting of the number of times a chosen scale is used. When you can measure what you are talking about and express in numbers, you know what you are talking about. But when you cannot measure it, when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely, in your thoughts, advanced to the stage of a science. 1.1.1 Why do we need to make a measurement? Suppose you go to the market to buy mangoes and they are priced at say Rs. 0.50 per kilogram. What would you expect the shopkeeper to do? Would you be happy if she gives you 4 or 5 small mangoes, which are surely less than a kilogram, and asks for the price of 1 kilogram? Similarly, the shopkeeper will also not like to give you more than a kilogram of mangoes for the price of a kilogram. An accurate measurement is desirable for both buyer and the seller. The absence of a suitable measurement may lead to conflicts between them. Measurement is an essential activity in our everyday life. You may ask why it is essential. Can't we do without it? Have you ever wondered how space scientists make sure that the space shuttle reaches the desired destination? Or when the shuttle comes back, it comes at a predetermined time and place. This is made possible by accurate measurement of many parameters and extensive calculations. For measurement, specific scale which is called unit. Lord Kelvin, 1824-1907. Measurement is science. Notes. 1.1.2 What is a unit? Imagine a situation. Suppose you are blindfolded and handed a bunch of currency notes. On counting them, you find that they are 46 in number. Can you tell how much money is in your hand? For knowing the exact amount of money, you need to know the denomination, i.e., whether the notes are of 10 rupees, Rs, 50, 100 rupees, or of some other denomination. Similarly, if you are told that 2 trees are 100 away from each other, how would you interpret it? Are the trees 100 centimeters, 100 feet, or 100 meters, or away? These examples suggest that the result of every measurement must be expressed in such a way that it makes a sense and has a unique meaning. For this, we need to know 2 things. Firstly, what measuring standard used, say centimeter, cm, meter, m, or foot in the above example, and the number of times it is used. The result of measurement of a physical quantity is expressed in terms of a value. The value of the physical quantity is equal to the product of the number of times the standard is used for the measurement and the quantity the standard defined for making the measurement. This defined a standard quantity, i.e., the scale used, e.g., meter or the foot in above case, is called a unit. Value of physical quantity equals numerical quantity x unit. A unit is a measure, device, or scale in terms of which we make physical Measurement. The value of a physical quantity consists of two parts, a numerical quantity and a unit, and is equal to their product. Thus, it is necessary to state the numerical quantity as well as the unit while expressing the result. So by now we know that the measurements are essential in every sphere of human activity and also that we need a unit or standard in terms of which we make the measurement and express the result of such a measurement. Let us learn about the characteristics of such a unit. What qualities should a unit have? 1.1.3 Characteristics of a unit. Can we measure the distance in kilograms? Obviously not. It is ridiculous to measure distance in terms of kilogram. It has no relevance for measuring distances. So to be useful, a unit should be relevant for the quantity being measured. Further, the unit used should be convenient also. Would it be convenient to express the distance between two cities in inches? Don't you think that kilometer would be a better unit? In addition to being relevant and convenient, a unit should also be well defined, i.e., it should be well understood by other people. For example, I express the distance between my house and a nearby shop as 200 steps. In order to make some sense, we need to define the step, whether it is my step or an adult and child. Is it while walking slowly or while running fast? How long is the step? Thus, to be useful, a unit must be number 2, relevant. Number 2, convenient. Number 2, well defined. Measurement is science. Notes. In today's world, an accurate measurement is a necessary. We have innumerable devices to make such measurement. You would be surprised to know that an atomic clock is so accurate that it may make an error of just 1 second in about 15 million years. Have you ever thought how our ancestors made measurements? What were the devices used and what the units of measurement? Let us try to learn about the interesting way measurements were made and also the way the system of measurement has evolved since then. However, why don't you assess your understanding of the meaning and need of measurement and about the units and their characteristics? INTEXT questions 1.1. 1. Define the term measurement by giving 2 examples. 2. What is a unit? 3. List the essential characteristics of a unit. 1.2. How did our ancestors make measurements? The need for measurement and measuring devices dates back to antiquity. When the humans became civilized, started cultivating and living in communities, they realized that one cannot do everything and they need to be interdependent. This paved the way for trade and then probably a need of a measure was felt. Various ways of measurements were adopted. The system of measurement has evolved a lot since then. Let us have a brief account of interesting means of measurement used by our forefathers. Figure 1.1. Use of body parts for measurements. The recorded history shows ample evidence that the different parts of the human body were used as a point of reference while making measurements. Some of these were digit, the width of a single finger; foot, the length of a foot; cubit, length of an arm; hand span, the distance between the tip of the thumb and the tip of the little finger when the hand is fully stretched out. Similarly, fathom meant the distance hand. Thumb. First finger. Hand span. Measurement is science. Notes. Between the ends of the hands of an Anglo-Saxon farmer when his arms were fully outstretched. It is interesting to note that these are still used sometimes. Certain historical units were based on the things around us. A.G. Romans used a unit called pace, which was equal to the stride of their army contingent, and they called the distance traveled by it in 1,000 paces to be equal to a mile. Similarly, the grain was used as the unit of mass in 16th century and was equal to the weight of a wheat grain. Based on the criteria given under section 1.1.3, evaluate the above units. What are the limitations you find in above ancient units of measurement? Write your response in the space given below. The following activity may help you to respond to the above query. Perform the following activity and then revisit your response above. Activity 1.1. Can you check the accuracy of the measurements using parts of your body as a unit? Personal Contact Program (PCP). You can perform this. Take a blackboard or a table, a desk, a wall, or any other suitable reasonably long object with group of 4 to 5 learners. First, measure the length of the blackboard using hand span and digits as the units of measurement and record your observations in the table given below. No. Name of the learner: length of the blackboard asterisk in hand span and digits, e.g. 10 hand spans. And 3 digits. 1, 2, 3, 4, 5. Asterisk or any other object on which the measurement is made. This activity can be performed in the class or even at home. In the class, a group of 4 to 5 students can participate in it. At home, the family members or friends can do the same. Measurement is science. Notes. The group to make the same measurement one by one and record their results in the table above. Thus, you can record your body cannot be used for accurate measurements based on your observation. Take the right option and delete the incorrect one. Would you like to revisit your response given above and revise? 1.2.1 Need for a standard unit. As you would have concluded from the activity given above, the units based on parts of human body are arbitrary and accurate. The results of the measurements vary from person to person because size of the unit is different for different person. For example, the units like a cubit or a foot would depend on the person making measurement. This created problems in trade between different countries and obviously in the day-to-day transactions. In order to overcome the limitations of body parts as units and to bring about uniformity in the measurement system, the need for exact measurement was felt. For this, a standard of measurements had to be developed which is acceptable to everybody. The problem of measuring lengths accurately was first solved by the Egyptians as far back as in 3000 BC. It was done by defining the standard cubit. It was defined to be equal to the distance between the elbow and tip of the middle finger of the pharaoh ruling Egypt at that time. Measuring sticks of length exactly equal to that of standard cubit were made. In this way, they made sure that the cubit was the same length all over Egypt. Similar efforts were made by other rulers also. For example, the British King Henry I, 1100-1137, decreed that a yard would exactly be equal to the distance from the top of his nose to the end of his thumb on outstretched arm. Queen Elizabeth I declared a mile to be exactly equal to 8 furlongs. A furrow long was the distance a pair of oxen could plow in a field without stopping to rest. It was found to be 220 yards. These standards proved to be useful but were short-lived, as once a given ruler went out of power or died, the system was not followed and a newer system came into being. Further, since different countries and the different provinces in a given country were governed by different rulers, they followed different systems of units. As a consequence, by the 18th century, a large number of units for mass, length, area, and volume came to be in widespread use. Let us now learn about the systems of units followed in India in different historical periods. 1.2.2 Indian Measurement System. The measurement system in India also has evolved a great deal from the ancient times. A. Indian measurement system in the ancient period. In aims to know the approximate time of the day. Long time durations were expressed measurement as science. Notes. In terms of the lunar cycles, which even now is the basis of some calendars. Excellent examples of measurement practices in different historic periods are available. For example, about 5,000 years ago in the Mohenjo-daro era, the size of bricks all over the region was same. The length, breadth, and width of bricks were always in the ratio of 4:1 and taken as a standard. Similarly, around 2,400 years ago, during the Chandragupta Maurya period, there was a well-defined system of weights and measures. The government at that time ensured that everybody used the same weights and measures. According to this system, the smallest unit of length was 1 parmanu. Small lengths were measured in annuals. For long distances, yojan was used. 1 yojan is roughly equal to 10 kilometers. Different units of measurements used in the period of Chandragupta Maurya. 8 parmanas equals 1 rajakan dust particle from the wheel of a chariot. 8 rajakans equals 1 liksha egg of lice. 8 likshas equals 1 yukamadhya. 8 yukamadhyas equals 1 yavamadhya. 8 yavamadhyas equals 1 angul. 8 anguls equals 1 dhanurmushti. Reference: Kautilya's Arthashastra. The Indian medicine system, Ayurveda, also had well-defined units for the measurement of the mass and volume. The measurement system was strongly followed to ensure the proper quantity of medicine for particular disease. B. Indian measurement system in the medieval period. In the medieval period also the measurement system was in practice. As described in Ain Akbari by Abul Fazl I Alami, during the period of Mughal Emperor Akbar, the gaz was used as the unit of measuring length. Each gaz was divided into 24 equal parts and each part was called tessuj. This system was extensively used to measure land pieces for construction of buildings, houses, wells, gardens, and roads. You should know that the gas was widely used as a unit of length till the metric system was introduced in 1956. Even today, in many parts of our country, particularly in the rural areas, gas is being used as a unit of length. See Indian measurement system during British period. In order to bring about uniformity in the system of measurement and the weights used, a number of efforts were made during the British period. British rulers wanted to connect Indian weights and measures to those being used in Great Britain at that time. During this period, the inch, foot, and yard were used to measure length, whereas measurement is science. Notes. Grain, ounce, pounds, etc. were used to measure mass. Included ritti, masher, tola, chatank, seer, and mount. Rati is a red seed whose mass is approximately 120 milligrams. It was widely used by goldsmiths and by practitioners of traditional medicine system in India. Relation between various units of mass used during the British period. 8 ritti, 1 masher, 12 masher, 1 tola, 5 tola, 1 chatank, 16 chatank, 1 seer, 40 seer, 1 mount. 1 mount, 100 pounds troy exact. INTEXT questions 1.2. 1. Name the smallest unit of length during the Chandragupta Maurya period. 2. List the parts of human body which can be used for measurements. 3. Why cannot the parts of human body be used for accurate measurement? 4. In which period was gas introduced as a unit to measure? 1.3 The modern measurement systems. Immediately after the French Revolution 1790, the French scientists took lead in establishing a new system of weights and measures. They advocated the establishment of national standards for the purpose and the use of decimal arithmetic system. This led to the birth of metric system, which, like a Hindu-Arabic counting system, is based on the multiples and subdivisions of 10. After detailed deliberations, the basic unit of length and mass were defined and their working standards were prepared. The working standard for meter was prepared by marking two lines a meter apart on a platinum iridium bar. Similarly, a platinum iridium cylinder was constructed, equal to the mass of 1 cubic decimeter of water, as the working standard for mass. These two standards have been preserved at the International Bureau of Weights and Measures at Serves near Paris. The copies of these were prepared and sent to different countries. As regards the time, the concept of hour, minute, and second based on the meter was defined as 1/10,000,000th, 1/10,7 of the distance between North Pole to the equator on the meridian running near Dunkirk in France and Barcelona in Spain. Measurement is science. Notes. The rotation of Earth was retained. An international treaty called Meter Convention was signed in 1875 to follow metric system throughout the world for trade and commerce. In the course of development of units, a number of systems were adopted. Two systems which were extensively used were the CGS and MKS systems. The CGS system was based on centimeter, gram, and second as the units for length, mass, and time, while MKS system used meter, kilogram, and second for the same. In 1958, it was realized that the units defined as standard needed to be redefined. Since 1983, it is defined as the length of the path traveled by light in vacuum in 1,299,792,458 of a second. The new exercise of redefining the system of units led to the birth of SI system of units, which is currently the system in use. Let us learn the SI system in details. 1.4C units. An international system of units called SI units was adopted at the 11th General Conference on Weights and Measures (CGPM) in 1960. SI is an abbreviation of the French name, Le Système International Units. You know that measurements are concerned with quantities like length, mass, time, density, etc. Any quantity which can be measured is called a physical quantity. The SI system of units is based on corresponding to 7 base physical quantities. These are the physical quantities in terms of which other physical quantities can be measured. The names and symbols of the base physical quantities and their corresponding SI units are given in Table 1.1. The precise definitions and the standards for the base SI units are given under Appendix I. Table 1.1 names and symbols of the quantities and the corresponding SI units. Base physical symbol of name of SI symbol for quantity physical quantity unit SI unit. Length L meter M mass M kilogram kilogram time T second S electric current I ampere thermodynamic T Kelvin K temperature. Amount of N mole more substance. Luminous I candela CD intensity. Note, the other measurements for temperature are in degrees Celsius, degree C, and Fahrenheit F. The base SI units are independent of each other. Measurement is science. Notes. Perhaps you may be confused by mass and amount of substance and also with luminous intensity as given in Table 1.1. The mass of a body is the amount of matter contained in the body, while a mole is the amount of any substance equal to its molecular mass expressed in grams. For example, 1 mole of HCl equals 36.46 grams. 2 moles of HCl equals 36.46 times 2 equals 72.92 grams. Luminous intensity is the amount of light emitted by a point source per second in a particular direction. Activity 1.2. Take a thermometer at your home. Observe the measuring marks on a thermometer along with a parent. I write down the two types of measuring marks indicating on the thermometer. E. Measure your temperature and record it in degree C, degree Celsius, and F. Fahrenheit E. In case you find it difficult to understand, you can contact your nearest doctor. On nurse name note, commonly, body temperature between 98.2 degrees Fahrenheit 98.6 degrees Fahrenheit is expressed in Fahrenheit. 1.4.1 Derived units. The base of fundamental SI units like length, mass, time, etc. are independent of each other. The SI units for all other physical quantities such as area, density, velocity can be derived in terms of the base SI units and are called derived units. In order to find the derived unit for a physical quantity, we have to find out the relationship between the physical quantity and the base physical quantities. Then substitute the units of the base physical quantities to find the. Let us take some examples to learn how to derive units for physical quantities in terms of base units. Example 1. Derive the SI unit for area of a surface. In order to derive the unit, we need to find out the relationship between area and the base physical quantities. As you know that the area of a surface is the product of its length and breadth. So, as the first step, we write area as area equals length times breadth. Since breadth is also a kind of length, we can write area equals length times length. Measurement is science. Then to find the derived unit for area, we substitute the units of the base physical quantities as unit of area equals meter times meter equals meter 2 equals m2 plus. The SI unit of area is m2 and is pronounced as square meter. Similarly, you can check that volume would have the SI unit as m3 or cubic meter. Example 2. Find the derived unit for force. You know that force is defined as force equals mass times acceleration equals mass times change in velocity time, since change in velocity equals length time. So, force equals mass times length time times 1 time equals mass times length time 2. The SI unit of force can be found by substituting the SI units of the base physical quantities on the right side of the expression. Thus, SI unit of force equals kilogram meter per second 2 equals kilogram ms minus 2. Some commonly encountered physical quantities other than base physical quantities, their relationship with the base physical quantities and the SI units are given in Table 1.2. Table 1.2. Some examples of derived SI units of the commonly used physical quantities. Derived quantity dimensions, name of unit, symbol of the unit. Area length times length square meter m, volume length times length cubic meter m3, speed, velocity length time meter per second ms minus 1, acceleration length time meter per second squared ms minus 2, wave number 1, length reciprocal meter m minus 1, density mass length 3 kilogram per cubic meter kilogram m minus 3, work mass times length 2 time 2 kilogram square meter kilogram m2 per second 2 per square second. A number of physical quantities like force, pressure, etc. are used very often, but their SI units are quite complex. Due to their complex expression, it becomes quite inconvenient to use them again and again. The derived SI units for such physical quantities have been assigned special names. Some of the physical quantities whose SI units have been assigned special names are combined in Table 1.3. Measurement is science. Notes. Table 1.3 names and symbols of the derived SI units with special names. Physical quantity derived SI unit, special name assigned, symbol assigned to the unit, the special name. Frequency S-1 Hz, Hz force m.kg, S-2 Newton, and pressure or stress m-1 kilogram, S-2 Pascal, power energy or work kilogram m2, S-2 joule J power kilogram m2, S-3 watt W. INTEXT questions 1.3. 1. Differentiate between base units and derived units. 2. What is the difference between mass and amount of a substance? 3. Derive the unit of pressure. Pressure equals force area. 4. Which term of measurement is commonly used by the announcer of your favorite radio program? 5. Observe a bulb tube light at your home for the unit measurement written on it. From Table 1.3, find out the physical quantity it measure. 6. Veena, Mohinder and Alam went to market. Veena brought milk with a liter measure. Mohinder brought ribbon by a measuring mark on the table, and Alam brought vegetables using stones. Which of them did not use the appropriate measurement while purchasing goods? Explain while given the names of right measurement. 1.4.2 SI prefixes. When we make measurements of physical quantities, quite often the quantity being measured is too large as compared to the base unit of the physical quantity. Look at some of the following examples. Mass of Earth equals 5,970 sextillion kilograms. Radius of Sun equals 696,000 OOM. Approximate distance between Mumbai and Delhi equals 1,400,000 meters. Other possibility is that the physical quantity is too small as compared to the base unit of the physical quantity. Look at some of the examples. Radius of a hydrogen atom equals 0.000005 m. Mass of an electron Ma equals 0.000911 kilograms. Measurement is science. Notes. Quantity being measured is either too large or too small as compared to the standard unit, then the value of the physical quantity is quite inconvenient to express. The numbers given above can be simplified by using what is called scientific notation of numbers. In this notation system, we represent the numbers as power of 10. In this notation system, we can rewrite the above examples as mass of Earth equals 5.97 times 1024 kilogram. Radius of Sun equals 6.96 times 10 8 m. Approximate distance between Mumbai and Delhi equals 1.4 times 10 6 meters. Radius of a hydrogen atom equals 5 times 10 minus 11 m. Mass of an electron Ma equals 9.11 times 10 minus 31 kilogram. In scientific notation, the numbers become relatively easier, but are still not convenient because they carry exponents. In order to simplify the numbers, the SI system of units has recommended the use of certain prefixes. These prefixes are used along with the SI units in such a way that the physical quantity being measured can be expressed as a convenient number. The SI prefixes have been defined to cover a wide range of 10 to 24 to 10 plus 24 of a unit and are given in Table 1.4. Table 1.4, SI prefixes for multiples and submultiples of units. Multiple prefix symbol, submultiple prefix symbol. 1024 याद wide minus 1 deci p 10 21 zeta z 10 minus 2 centi circa 10 18 exa a 10 minus 3 milli m 10 15 peta p 10 minus 6 micro m 10 12 tera t 10 to 9 nano n 10 9 giga g 10 minus 12 pico page 10 6 mega m 10 minus 15 femto f 10 3 kilo k 10 minus 18 atto 10 2 hecto h 10 minus 21 zepto z 10 1 decada 10 minus 24 yocto y. 1.4.3 How do we use SI prefixes? In order to use SI prefixes, we have to keep a basic rule in mind. The rule is that the prefix is chosen in such a way that the resulting value of the physical quantity has a value between 0.1 and 1000. Let us illustrate it with examples. Measurement is science. Notes. Radius of sun equals 6.96 times 10 8m equals 696 times 10 6m equals 696 megameters 696 megameter alternatively equals 6.96 times 10 8m equals 0.696 times 10 9m equals 0.696 gigameters 0.696 gigameter. INTEXT questions 1.4. Rewrite the following measurements of length using suitable SI prefixes. I. Effective radius of a proton, 1.2 times 10 minus 15 meters, blank D. Radius of human red blood cell, 3.7 times 10 minus 6 meters, blank D. Radius of our galaxy, 6 times 19m, blank. You must follow the following rules while using SI prefixes. Note. Number 2. No space is required between the prefix and the symbol of the unit e.g. nanogram is written as ng and not as ng. Number 2. The prefixes are used only with the units and not alone, e.g. 10 mu does not convey anything. It has to be 10 micrometers, 10 micrograms, etc. Number 2. You can use only one prefix at a time, e.g. 10 minus 12 G is represented as 1 pg and not as ws1 millilligram. Number 2. SI prefix is not used with the unit degree C. Number 2. The prefixed unit as raised applies to the whole unit, including the prefix, e.g. 1 kilometer 2 equals 1000 meters. 2 equals 10 6 meters 2 and not 1000 meters 2. Having learned about the base SI units, the method of obtaining the derived SI unit for a given physical quantity, and also the need and usage of prefixing SI units, let us now learn about the grammatical rules for using SI units in general. 1.4.4 Rules for representing SI units. The SI units are the result of the attempt of scientists to evolve a common international system of units that can be used globally. It is therefore important that the words and the grammar is logical and defined unambiguously, i.e. everyone uses the system of units in the same manner. In order to achieve this objective, a number of grammatical rules have been framed. The most commonly used rules are given below. Number 2. While writing the value of physical quantity, the number in the unit is separated by a space. For example, 100 milligrams is correct but not 100 milligrams. Number 2. No space is given between number and degree C, degree, minute and second of plane. Angle. Number 2. The symbols of the units are not changed by writing them in plural, e.g. 10 milligrams is correct but not 10 mgs. Measurement is science. Notes. Number 2. The symbols of the units are not followed by a full stop except at the end of a sentence. 10 milligrams of a compound is incorrect. Number 2. In writing the SI unit obtained as a combination of units, a space is given between the symbol. Thus, ms represents meter second while ms stands for millisecond. That is, if giving any space, the first letter may be taken as a prefix. Number 2. For numbers less than unity, 0 must be inserted to the left of the decimal point. E.g. writing 0.928 grams is correct but not 0.928 grams. Number 2. Symbols of units derived from proper names are represented by using capital letters. When written in full, the unit should not be written in plural, e.g. 30.5 joule or 30.5 J is correct but 30.5 joules or 30.5 J is not correct. Number 2. When using powers with a unit name, the modifier squared or cubed is used after the unit name, e.g. second squared, gram cubed, etc. Area and volume are exception in such cases. The qualifier for the power comes first, e.g. square kilometer or cubic centimeter, etc. Number 2. For representing unit symbols with negative exponent, the use of the solidus sign should be avoided. If used, no more than one solidus should be used, e.g. the unit for gas constant, J minus 1 mole minus 1 may be represented as J Kelvin mole but not as J per Kelvin per mole. The rules mentioned earlier for the use of SI prefixes are to be followed along with these rules. What you have learned. Number 2. Measurement is a basic skill which forms an essential part of our day-to-day activities irrespective of what we do. Number 2. It is a process of comparison and involves counting of the number of times a chosen scale is used to make the measurement. Number 2. Measurement is essential for accurate determination of a physical quantity. It is helpful in day-to-day transactions, trade and scientific endeavors. Number 2. The unit of physical quantity is a standard value in terms of which other quantities of that kind are expressed. Number 2. To be useful, a unit must be relevant to the quantity being measured, be convenient and also well defined so that it is understood by everybody in an unambiguous way. Number 2. In the ancient times, parts of human body were used for measurement, but these led to conflicts and confusions because these were arbitrary, non-uniform and led to results which were not reproducible. Measurement is science. Notes. Number 2. Currently, we follow an international system of units called SI units. This system is based on 7 base units which correspond to 7 base physical quantities, namely length, mass, time, temperature, amount of substances, light intensity, and electric current. Number 2. The units for all other physical quantities can be derived in terms of the base SI units and are called derived units. Some of the derived units have been given special names. Number 2. SI prefixes are used in cases where the quantity being measured is too large or too small as compared to the base unit of the physical quantity. Number 2. The grammar of SI units must be followed while writing them. Terminal exercise. 1. Which of the following is not an SI unit? A meter B pound. C kilogram B second. 2. If the mass of a solution in 10 micrograms, it is the same as A 10 minus 6 G B 10 minus 12 G. C 10 minus 9 G D 10 minus 3 G. 3. Indicate whether the following statements are true or false. Write T for true and F for false. SI units are arbitrary. E1 mm 2 equals 10 minus 3 m2. E10 to 15 G equals 1 mpg. SI unit for pressure is Pascal. 4. Represent the following measurements by using suitable SI prefixes. I2 times 10 minus 8 s e 1.54 times 10 minus 10 meters e 1.98 times 10 minus 6 mo IV 200,000 kilograms 5. Give the SI units used while buying. A silk ribbon B milk. C potatoes. 6. Give the common unit to measure our body temperature and write its SI unit 7. What are the advantages of SI units? A. Mass. The SI unit of mass is kilogram. 1 kilogram is the mass of a particular cylinder made of platinum iridium alloy kept at the International Bureau of Weights and Measures in France. This standard was established in 1887 and measurement is science. Notes. There has been no change because this is an unusually stable alloy. Prototype kilograms have been made out of this alloy and distributed to member states. The national prototype of India is the kilogram number 57. This is preserved at the National Physical Laboratory, New Delhi. B. Length. The SI unit of length is meter. Earlier, the meter, also written as meter, was defined to be 1/10 7 times the distance from the equator to the North Pole through Paris. This standard was abandoned for practical reasons. In 1875, new meter was defined as the distance between two lines on a platinum iridium bar stored under controlled conditions. Such standards had to be kept under severe controlled conditions. Even then, their safety against natural disaster is not guaranteed, and their accuracy is also limited for the present requirements of science and technology. In 1983, the meter was redefined as the distance traveled by light in vacuum in a time interval of 1,299,792,458 of a second. This definition establishes that the speed of light in vacuum is 299,792,458 meters per second. C. Time. The SI unit of time is second. The time interval second was originally defined in terms of the time of rotation of Earth about its own axis. This time of rotation is divided in 24 parts. Each part is called an hour. An hour is divided into 60 minutes and each minute is subdivided into 60 seconds. Thus, 1 second is equal to 186,400 th part of the solar day. But it is known that the rotation of the Earth varies substantially with time and therefore, the length of a day is a variable quantity, may be very slowly varying. The 13th General Conference on Weights and Measures in 1967 defined 1 second as the time required for cesium-133 atom to undergo 919263177 vibrations. The definition has its roots in a device which is named as the atomic clock. Heat temperature. The SI unit of temperature is Kelvin K. The thermodynamic scale on which temperature is measured has its zero at absolute zero and has its lower fixed point corresponding to 273.15 kelvins at the triple point of water 0 degrees Celsius. 1 unit of thermodynamic temperature, 1 Kelvin, is equal to 1,273.15 of the thermodynamic temperature of the triple point of water. A. Electric current. The SI unit of electric current is the ampere. A. 1 ampere is defined as the magnitude of current that when flowing through two long parallel wires, each of length equal to 1 meter, separated by 1 meter in free space, results in a force of 2 times 10 minus 7 n between the two wires. F. Amount of substance. The SI unit of amount is mole. 1 mole is defined as the amount of any substance, which contains as many elementary units as there are atoms in exactly 0.012 kilogram of C12 isotope of carbon. G. Luminous intensity. The SI unit of luminous intensity, I, is candela CP. The candela is defined as the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 times 1012 Hz and that has a radiant intensity of 1683 watt per steradian in that direction. Measurement is science. Notes. Answers to INTEXT questions. 1.1. 1. Measurement may be defined as a kind of counting. It refers to counting of the number of times a chosen scale is used to make the measurement. For example, an inch tape to measure length, or a graded cylinder to measure volume. 2. A unit is a measure, device, or scale in terms of which we make physical measurement. 3. A standard unit must have the following characteristics to be useful. Number 2, relevant. Number 2, convenient. Number 2, well-defined. 1.2. 1. Parmanu. 2. Angul, cubit, etc. 3. Because the parts of human body may vary from person to person and we cannot trust on our senses to measure exactly and accurately. 4. During the period of Mughal Emperor Akbar. 1.3. 1. A. Fundamental units are only 7 in number whereas derived units are very large in number. B. Fundamental units are independent of each other but derived obtained from fundamental units. 2. Mass of a body is the amount of matter contained in a body while the amount of the substance is equal to its molecular mass. 3. Unit of pressure equals unit of force. Unit of area equals kilogram ms minus 2 per meter 2 equals kilogram m minus 1 s minus 2. 4. HZ. 5. Watt 6. Mohinder and Alam, meter scale kilogram. 1.4. I 1.2 FM E 3.7 millimeters E 68. For more information. Kahani Maap Tolki, Vigyan Prasar publication. Module 2. Matter in our surroundings. 2. Matter in our surroundings. 3. Atom and molecules. 4. Chemical reaction and equations. 5. Atomic structure. 6. Periodic classification of elements. 7. Chemical bonding. 8. Acids, bases and salts. Matter in our surroundings. 2. Notes. Matter in our surroundings. You have learnt about units of measurement in the previous lesson. What we eat, drink or breathe is the matter. Hence all of us are surrounded by matter. Anything which occupies space and has mass is matter. In order to understand the world better, it is necessary to understand the nature of matter. In this section, you shall learn about matter and shall utilize the concepts of measurement in understanding the properties of matter. Objectives. After completing this lesson, you will be able to: Number 2, describe what is matter and explain its particulate nature. Number 2, clarify and differentiate the 3 states of matter, solid, liquid and gas. Number 2, describe the effect of pressure and temperature on states of matter. Number 2, illustrate the interconversion of these states with the help of suitable examples. Number 2, classify the given matter as an element, a compound or a mixture. Number 2, distinguish between homogeneous and heterogeneous mixtures. Number 2, define the term solution, solvent and solute. Number 2, calculate the percentage composition of a solution. Number 2, describe the properties and uses of suspension. And number 2, describe the common methods used for separation of mixtures or purification of a substance. Matter in our surroundings. Notes. 2.1. What is matter? Matter is anything which has mass and occupies space. All solids, liquids and gases around us are made of matter. Scientists believe that matter is made of tiny particles that clump together. You cannot see these particles, but you can see the matter. For example, a book, a car, a letter, a handset, a piece of wood, tree, a bag, etc. Think and add a few more examples from your day-to-day life. When we say matter has mass, it means matter has weight. The heavier an object, the more mass it has. Matter occupies space, it means matter has volume. A substance is a pure kind of matter having only one kind of constituent particle, atom or molecule. Water, iron, gold, copper, aluminum and oxygen are examples of substances. All substances are matter, but all forms of matter are not substances. You must be wondering how this is possible. Well, a substance is a pure form of matter. That is, it is the same throughout. Let us take the examples of soft drinks and soil. In what category you would put them? They are not a single substance, but they are a mixture of substances. Now you will find out what's the nature of matter. 2.2. Particulate nature of matter. Human beings questioning the nature of matter. In ancient times, there were views about it. One school of thought believed that if we take a piece of matter, for example stone, and break it into smaller pieces and break these smaller pieces into still smaller pieces, the process can be repeated any number of times. This would happen because matter is continuous and its piece of any size can be broken or subdivided into smaller pieces. Greek philosophers Plato and Aristotle belonged to the school of thought. The second school of thought believed that process of subdivision of matter can be repeated only for limited number of times. A stage would be reached when the tiny particles of matter so obtained cannot be further subdivided. They believed that all matter is composed of very tiny particles. In other words, the matter has particulate nature. The smallest indivisible particles of matter were given the name atom from the Greek word atomos for indivisible. Indian philosopher Kanada and Greek philosophers Leucippus and Democritus belong to this school of thought. The term atom was coined by Democritus. Today, the idea of atom has changed since it was first proposed. The modern idea of atom originated with John Dalton in 1803. Today, we talk of two types of constituent particles, atoms and molecules. Atoms is a basic unit of matter and all chemical matter in our surroundings. Properties of matter can be explained on its basis. Molecules are important in explaining physical properties of matter. Details about atoms and molecules will be undertaken in the lesson number 3. Let us learn about how to classify matter. Notes. INTEXT questions 2.1. 1. What is matter? 2. Which of the following is not a pure substance? A. Iron. B. Water. C. Soil. 3. Who coined the term atom and what does it mean? 2.3 States of matter. Matter can be classified in many ways. However, the following are the two main ways of classifying the matter. I. By the physical state of matter is a solid, liquid, or gas, and D. By the chemical composition of matter is an element, compound, or mixture. We shall discuss these classifications in the next section. Let us discuss about the classification of matter based on physical states. Matter can ordinarily exist in 3 states: solid, liquid, and gas. These 3 states of matter have different properties. All the 3 states, namely steam or water, vapor, gas, water at room temperature, liquid, and ice, solid. This is the only substance which exists naturally in all the 3 states. The characteristic properties of different states of matter depend on intermolecular forces. The forces holding molecules together are called intermolecular forces. Intermolecular forces, i.e., forces between the constituent molecules, try to keep molecules together, but thermal energy always tries to keep them far apart. It is the competition between molecular interaction energy and thermal energy that decides whether a given substance under given conditions will be a solid, liquid, or gas. Thermal or heat energy can convert one state of matter into another state. Thus, a particular state of a matter depends on both intermolecular force and the thermal energy, which basically depends upon temperature. Each state of matter has some characteristic properties. Now you shall learn about these properties. Matter in our surroundings. Notes. 2.3.1 Solids. We are surrounded by innumerable solid objects. A piece of wood, a stone, a pencil, a pen, and a computer all are examples of solids. A solid has definite size and shape which do not change on their own. See Fig. 2.1. However, by using external forces, you can change the shape of a solid. For example, you can cut a piece of metal into 2 and you can use hammer to change its shape. Can you think of any other way to change the shape of solids? Yes, you can. Beat it into sheets or pull it into strings. Solid, liquid, gas. Figure 2.1 Shapes of different states of matter. In solids, the constituent particles are present very close to each other, and the intermolecular forces operating between the constituent particles are very strong, and they are capable of keeping the molecules in fixed positions. This is the reason why solids are rigid and hard. Also, solids cannot be compressed. The attractive intermolecular forces become repulsive when atoms or molecules are forced to come further closer. When a solid is heated, there is an increase in thermal energy of the particles, which results in conversion of solid into liquid. The temperature at which this happens is the melting point of the solid. 2.2 Liquids. Water is a liquid. Mustard oil and kerosene oil are other examples of liquids. Can you think of some more examples? A liquid has a definite volume. However, a liquid does not have a definite shape. It takes the shape of its container. A liquid can flow. You can pour a liquid or spill it. Can you spill a solid? Liquids have properties. Intermolecular forces in liquids are weaker than salts but stronger than gases. In liquids, the constituent particles do not occupy fixed position as in solids, but they have freedom of movement as in gases. In liquids, intermolecular forces are stronger than those of gases. The constituent particles, atoms, and molecules in a liquid can break away from each other and get attracted while approaching the other molecules. Like in solids, matter in our surroundings. Notes. The intermolecular forces become repulsive when an attempt is made to bring the molecules closer by applying pressure. This is the reason why pressure does not have much effect on volume of liquids. 2.3.3 Gases. We cannot see gases, but they are all around us. We can feel the presence of air. When the wind blows, the wind is moving air and is a mixture of many gases, like oxygen, nitrogen, argon, carbon dioxide, and others. The gas occupies the entire volume of the container irrespective of its size. See Figure 2.1. In gases, molecules move freely because the intermolecular forces are very weak and are unable to keep the gas molecules together in bulk. The molecules remain far apart from each other due to weak molecular interactions. Since molecules are far away from each other in gases, they can be brought closer when pressure is applied. This is the reason why gases are highly compressible. We can compress a gas only up to a certain limit. Beyond this limit, repulsion between gas molecules becomes very high. Temperature also affects the volume of the gases. When temperature increases, volume of the gas also increases. For example, when a closed container is heated, it blasts due to rapid increase in volume. We are lucky that a gas can be compressed easily. If this was not the case, then we could not have obtained CNG, compressed natural gas. As you might be aware that CNG is used as a clean fuel for vehicles, and you might have noticed that at the back of several auto rickshaws and buses, CNG is written. We also have our cooking gas cylinders in kitchen because gas LPG is compressible. There are many other examples of usage based on compressibility of gases. Can you think some more examples? Oxygen cylinder in hospital is another example. The distribution of molecules in solid, liquid, and gas is shown in Fig 2.2. Figure 2.2, schematic representation of distribution of molecules in solid, liquid, and gas. Matter in our surroundings. Notes. Three basic states of matter described above are dominant on Earth, but they become less relevant in other parts of the universe. You will be surprised to know that 99% of the matter in the entire universe is not a solid, a liquid, or a gas. The form of matter that is more dominant is called plasma. The sun consists of plasma as most of the other stars do. You will learn about plasma in your higher classes. Different characteristics of the three states of matter have been summarized in Table 2.1. Table 2.1, different characteristics. State of volume, density, shape, fluidity, compressibility, matter. Solid has fixed, high has definite, does not negligible. Volume, shape, flow, liquid has fixed, lower has no flows, very volume is definite, smoothly, small, compared, shape. To solid it takes shape of container. Gas has no low, has no flows, highly. Fixed, definite, smoothly compressible, volume, shape. INTEXT questions 2.2. 1. Which of the three states of matter has no definite volume? Give one reason for your answer. A. Solid. B. Liquid. C. Gas. 2. Why do solids have definite shape? 3. Name a substance which exists naturally in all the three states. There are two basic concepts in the physical world around which you can organize everything. These two basic concepts are matter and energy. Both matter and energy are related to each other by the formula A equals mc2. Here A is energy, m is mass, and c is velocity of light. One of the greatest scientists of all times, Albert Einstein, showed that matter can be transformed into energy, and energy can be transformed into matter. No doubt, transforming matter into energy is easy, whereas transforming energy into matter is difficult. Matter in our surroundings. Notes. 2.4 Effect of temperature and pressure on states of matter. Have you ever thought what happens if a solid substance is heated? When heat is supplied to a solid, it expands. This expansion is very small. In fact, after receiving thermal energy, particles, atom molecules vibrate more rapidly in their position and take up more space. If particles become more energetic on further heating, they leave their fixed positions and the solid melts. Once a solid becomes liquid, it can be poured into a container. As you learned earlier, a liquid takes the shape of the container in which it is poured. Particles in the liquid state are free to move. Now let us see what happens when a liquid is heated. On receiving heat, thermal energy, a liquid is converted into a gas. This happens because the kinetic energy of the particles becomes so high that they can overcome the intermolecular force within the liquid. Therefore, liquid is converted into gas vapor. Figure 2.3 Interconversion of states of matter. Figure 2.4 Interconversion of states from solid to liquid, liquid to gas, and vice versa with variation of temperature. Matter in our surroundings. Notes. When a gas is heated, kinetic energy of the particles increases. They move more freely and at much higher speed. Intermolecular distance also increases and the volume of the gas increases if pressure is kept constant. Do you know what happens when a balloon filled with air is brought near fire? A pure solid turns to liquid at a fixed temperature, or in other words, conversion of pure substance from solid to liquid takes place at one particular temperature. This particular temperature is called melting point of that particular solid substance. Similarly, when the liquid cools down, it converts into solid at a particular temperature. This temperature is called freezing point of that particular liquid substance. The temperature at which a liquid boils and is converted into a gas is boiling point of the liquid. Activity 2.1. Demonstrating the interconversion of the three states of matter. Materials required: ice container, gas burner, or any other heating device. How to do it? Put the ice in the container and gradually heat it. First it will melt into water, and if you continue heating it will turn into vapor. You should remember that the three different states of matter respond differently with changes of temperature and pressure. All the three states expand or show an increase in volume when the temperature is increased. Increase in volume when the temperature is lowered. However, the effect of solid and liquid is negligible. A gas can be compressed easily by applying pressure. Activity 2.2. You can observe the effect of pressure on gases and liquids by performing the following experiment. Take a syringe and close its nozzle by inserting it in a rubber cork. Remove the piston so that the entire space inside the syringe is filled with air. Now, insert the piston carefully back in the syringe and try to compress the air by pushing the piston. What do you observe? You will find that the piston can be pushed easily. Of course, beyond a point, you will not be able to push the piston. This shows that air is compressible easily. Now you repeat the experiment with liquid. Can you push the piston as easily as you could push with air? If you try, you will find that it is not possible. This is because the molecules in liquids are much close to each other as compared to gases. Matter in our surroundings. Notes. Figure 2.5 Effect of pressure on gas and liquid. INTXT questions 2.3. 1. Why gases are more compressible as compared to solids? 2. How can you change water into ice? 2.5 Elements, compounds and mixtures. 2.5.1 Elements. All substances are made up of chemical elements. A chemical element is a basic form of matter that cannot be chemically broken down into simpler substances. A chemical element is a pure substance and it consists of one type of atom distinguished by its atomic number. Example elements are helium, carbon, iron, gold, silver, copper, aluminum, hydrogen, oxygen, nitrogen, sulfur, copper, chlorine, iodine, uranium, and plutonium. Elements are the building blocks of the universe. In total, 114 elements have been listed so far. Out of the total 114 known elements, about 90 occur naturally on Earth and the remaining have been synthesized artificially by nuclear reactions. Only two elements, namely hydrogen 92% and helium 7%, make up about 99% of the total mass of the universe. The remaining elements contribute only 1% to the total mass of the universe. Out of about 90 elements found naturally on Earth, two elements, silicon and oxygen, together make up almost 3/4 of the of elements, but the composition of elements in human body is very much different from that of the Earth's crust, as it can be seen from table 2.2. Liquid. Same level. Before after. Gas piston. Piston. Gas. Before after pressure. Pressure. Pressure pressure. Matter in our surroundings. Notes. Table 2.2 Elements in Earth's crust and human body. Elements percent by mass. Earth's crust, human body. 1. Aluminium 6.5 very little. 2. Calcium 3.6 1.5. 3. Carbon 0.03 18.5. 4. Hydrogen 0.14 9.5. 5. Iron 5.0 very little. 6. Magnesium 2.1 0.1. 7. Oxygen 46.6 65.0. 8. Silicon 27.7 very little. 9. Sodium 2.8 0.210. Sulfur 0.03 0.3. Although human beings and Earth share elements in their composition, human beings have several advantages like being able to think, feel, etc. Don't you think that it is our responsibility to take care of Earth? 2.5.2 Compounds. A compound is a substance formed when two or more than two elements are chemically combined. A compound can be defined as a pure substance made from two or more elements chemically combined together in a definite proportion by mass. When elements join to form compounds, they lose their individual properties. Compounds have different properties from the elements they are made of. For example, water, a compound, is made up of elements hydrogen and oxygen, but properties of water are different from those of hydrogen and oxygen. The world of compounds is really fascinating because compounds show a great variety in forms and properties. Some examples of compounds are given below. Glucose, glycerol, calcium oxide, sodium chloride, sulfuric acid, carbon dioxide, acid, sodium carbonate, ethanol, carbon monoxide, phenol, citric acid, methane. A pictorial representation of element, compound, and mixture is shown in figure 2.6 Matter in our surroundings. Notes. Figure 2.6 A pictorial representation of elements, compounds, and mixtures. From the figure we can see that elements combine to form compounds, but in the mixture elements and compounds maintain their separate identities. 2.5.3 Mixture. In our everyday life we deal with a large number of substances, but majority of them are not pure substances, elements, or compounds. They are mixtures of two or more pure substances. In the next section we shall see that there are two types of mixture depending on whether the parts of the mixtures completely mix or not. The relationship among elements, compounds, and other categories of matter are summarized in figure 2.7. M. IXTURAS. COM. POUNDS. ALAN. A. Hydrogen H molecules 2. Water H2O molecules. Mixture of hydrogen and oxygen. Oxygen O molecules 2. Hydrogen peroxide HO molecules 2. Mixture of hydrogen peroxide and water. Matter in our surroundings. Notes. Figure 2.7 Classification of matter. INTEXT questions 2.4. 1. Classify the following into element, compound, and mixture: aluminum, carbon, granite, water, silicon, carbon dioxide, air, and sugar. 2. How does an element differ from a compound? 3. Which is the most abundant element in the universe? 2.6 Homogeneous and heterogeneous mixtures. Mixtures are broadly divided into major groups: I. Homogeneous mixtures and E. Heterogeneous mixtures. 2.6.1 Homogeneous. You have seen that people having loose motion take over. In some mixtures, constituents are completely mixed in such a way that the entire mixture has the same composition throughout. Such mixtures which have uniform composition are called homogeneous mixtures. For example, when you prepare sherbet by mixing sugar and water in a jug, the entire mixture has the uniform matter in our surroundings. Notes. Sweetness. Technically, such homogeneous mixtures are called solutions. For example, common salt, which is solid when dissolved in water, forms a liquid mixture or a salt solution. The salt is totally dispersed into water uniformly and one cannot see it. Figure 2.8. 2/3 of the Earth's surface is covered by seawater, which is nothing but a homogeneous mixtured solution of various salts in water. Seawater also contains dissolved gases like oxygen and carbon dioxide. The air we breathe is a homogeneous mixture of different gases. Two liquids can also form homogeneous mixture. For example, water mixes with ethyl alcohol in all proportions. In other words, water is miscible with ethyl alcohol or vice versa. Many alloys are also homogeneous mixtures of two or more than two metals. Gold and copper form homogeneous solid solution. Do you know a goldsmith can judge the purity of gold by testing any part of it? Common salt, water, glass rod, homogeneous. Mixture of common salt and water. Figure 2.8. Mixing of common salt into water is a mixture where the substances are completely mixed together and have uniform composition throughout. Different types of homogeneous mixtures that may result by mixing different substances have been summarized in Table 2.3. Table 2.3. Different types of homogeneous mixtures. Type of description. Examples. Can you think mixture? Other examples. Solid plus liquid. Solid dissolves in liquid to form transparent solution. Liquid plus liquid forms a single transparent mixture. Gas plus liquid. Gas completely dissolves in a liquid to form a transparent solution. Gas plus gas mixture of two or more gases. Solid plus solid. Some metallic alloys. You can discuss with your friends others while carrying out the above exercise. Sugar in water or salt in water. Iodine and ethyl alcohol. Tincture iodine. Mixture of water and ethyl alcohol. Soda, water, and any other common salt matter in our surroundings. Notes. 2.6.2 Heterogeneous mixture. Have you ever brought a mixture from market? If yes, then you must have noticed that such a mixture contains different constituents and each of these constituents is visible. Such mixtures where the constituents do not completely mix with each other and remain separate are called heterogeneous mixtures. Figure 2.9. In such mixtures, one substance is spread throughout the other in the form of small particles, droplets, or bubbles. Soil. Water. Heterogeneous mixture of soil and water. Mixing of soil into water to form heterogeneous solution. A heterogeneous mixture where the substances, parts, or phases remain separate and composition is not uniform. Different types of heterogeneous mixtures that may result by mixing different substances have been summarized in Table 2.4. Table 2.4. Different types of heterogeneous mixtures. Type of description. Examples. Can you think mixture of another examples? Suspension. Solid plus liquid. Gel. Liquid trapped in solid. Emulsion. Mixture of tiny droplets of one liquid suspended in another. Aerosol. Small droplets of liquid or particles of solid dispersed in a gas. Foam. Gas in liquid. Small bubbles of gas trapped in liquid. Gas in solid. Small bubbles of gas trapped in solid. Floor in water. River. Water carrying mud, fruit, jelly, agar, gel, milk. Clouds. Liquid in gas. Smoke. Solid in gas. Shaving foam. Polystyrene foam. Thermocol. Matter in our surroundings. Notes. You may like to discuss with your mother to know whether any of the above types of mixtures are used in your home. Activity 2.3. Collect at least 10 different things from your homes and surroundings and classify them based on their composition and place in the following table. S. No. Name of element, compound, mixture, not the things, known objects, homogeneous or material, heterogeneous. 1. Water. 2, 3, 4, 5, 6, 7. 1. Say whether ethyl alcohol and water form a homogeneous mixture or heterogeneous mixture. 2. Give an example of homogeneous mixture obtained by mixing two solids. 2.7 Solution and its concentration of solution. A homogeneous mixture is formed when one or more substances A. Solute are completely dissolved in another substance, the solvent. When we think about solutions, the most common examples that come to our mind are the solutions that are obtained by dissolving solids in water. Sugar or common salt dissolved in matter in our surroundings. Notes. Water gives this type of solution. Do you know that 2/3 of the Earth's surface is covered by a solution? You may be able to guess the solution present in oceans. The sea water is also contains gases like and carbon. Such dissolved gases are very important for life to survive in oceans. There are some solutions of 2 or more than 2 liquids. As you know that ethyl alcohol mixes with water in all proportions to form a solution. Iodine solid dissolved in ethyl alcohol gives tincture of iodine which has antiseptic properties. A solution made of solid dissolved in a liquid has 2 parts. Number 2. The solid that dissolves is called the solute. Number 2. The liquid in which the solid is dissolved is called the solvent. Figure 2.1. Solute. Solvent. Figure 2.10 mixing of alcohol into water. You have just seen that solutions are not confined to only solids dissolved in liquids. There are other types of solutions as described earlier. In each case, the substance which is present in bigger quantity is normally taken as solvent and substance which is present in smaller quantity is normally taken as solute. When a substance dissolves in a solvent, it is said that that particular solute is soluble in that particular solvent. If it does not dissolve, then it is insoluble. Water is a commonly used solvent as it dissolves a large number of substances. Because of this property, water is called a universal solvent. Different types of substances dissolve in water. Because of this unique property of water, plants can take minerals from the soil. Being a good solvent, water is used in many ways. However, there are some disadvantages also which result from this unique property of water. Water becomes easily contaminated. Therefore, purifying water for drinking and other uses is a major challenge. There are other important solvents, for example, the organic liquids. The organic solvents are important because, unlike water, they dissolve organic substances. Ethyl alcohol and benzene are examples of such organic solvents. Matter in our surroundings. Notes. 2.7.1 Concentration of a solution. The term concentration is most often used when we talk about solutions. Concentration of a solution is expressed in terms of the amount of solute present in a given mass or in a given volume of a solvent. Usually, concentration of a solution is defined as the mass of solute present in a definite volume of a solution, which is usually taken as 1 liter. Concentration of a solution may also be expressed in terms of percent by mass of solute in gram. This gives the mass of solute per 100 units grams of solution as shown below. Percent of solute equals mass of solution times 100. A solution of 10% glucose by mass means that 100 solution contains 10 gram of glucose. This means 10 grams of glucose is dissolved in 90 grams of water. When we try to dissolve a particular substance, say sugar, in water, the solution becomes more concentrated as we add more and more sugar. A concentrated solution contains a high proportion of the solute. A dilute solution contains a small proportion of solute. If we keep on adding solute to a solvent, keeping the temperature constant, we reach a point where no more solute will be dissolved. At this point, we say that the solution has become saturated with respect to solute. Temperature. More solute will get dissolved. The concentration of a solute in a saturated solution at a definite temperature is called solubility of that solute in that particular solvent. Activity 2.4. Make a solution of sodium chloride in water with a known concentration of 10 grams liter by mass. 1. Take a graduated flask and fill approximately half with distilled water, the solvent. 2. Weigh out 10 grams of sodium chloride, the solute. 3. Carefully add the sodium chloride to the water in the container. 4. Gently shake the container to dissolve all the sodium chloride. 5. Add more distilled water to make up the volume of the solution to exactly the 1000 milliliters 1.0 decimeters streak mark on the neck of the graduated flask. Finally, shake the flask carefully to make the solution uniform. Matter in our surroundings. Notes. INTEXT questions 2.6. 1. To make 1 kilogram 40% sugar solution by mass, how much sugar and water will you need? Sugar. Water. 2. What is the name given to a liquid which dissolves a solid to make a solution? 3. To make a given solution more concentrated, what will you add? 2.8 Suspensions. In winter, the fog is a common experience in both urban and rural areas. What is fog? Fog forms when tiny water droplets are suspended in air. So fog is nothing but a type of a suspension. There are large numbers of substances which do not mix with each other. There are some solids that do not dissolve in water or other liquid solvents, and there are liquids that do not mix with each other. The mixing of such substances results into heterogeneous mixtures. Depending on the size of the particles suspended or dispersed in the surrounding medium, heterogeneous mixtures can be divided into colloids and suspension. You will study about colloids in higher classes. Here we shall briefly describe suspension. Materials of smaller particle size and soluble in a solvent but visible to naked eyes form suspension. Unlike a colloid, which contains smaller particles ranging in size from 1 to 1000 nanometers, a suspension contains relatively larger particles. The size of particles in suspension is over 1000 nanometers. When flour is added to water, it does not dissolve but forms a slurry, which we call a suspension. However, if less amount of water is added in the flour, 200 grams of flour and 100 milliliters of water, we get dough to make chapati etc. Muddy water is an example of suspension. When a suspension is allowed to stand undisturbed, the dispersed particles settle down. Figure 2.11. Before after. Figure 2.11 settling of suspension when it is allowed to stand undisturbed. Matter in our surroundings. Suspensions are very useful in medical sciences. For example, barium sulfate, whose solubility is very low when dispersed in water, is an opaque medium. It is used for diagnostic X-rays barium meal test. Many medicines which are insoluble in water are given in the form of suspension, for example, penicillin and amoxicillin. Please check a few bottles of medicine. Do you find the word suspension written on a bottle? Notes. Activity 2.5. Prepare a suspension using materials available in your home. Materials required: wheat flour 1 cup, approximate 200 grams, water a glass, 250 milliliters, and a spoon. How to do it? Pour water into a glass and add wheat flour to water. Stir the water with the help of the spoon. Keep the mix undisturbed for some time. Write your observation and identify whether you have prepared a suspension or a solution. Give at least one reason for your answer. 2.9. Separation of mixtures. Have you seen someone removing unwanted materials from rice or wheat? If so, then you have seen separation of heterogeneous mixture into pure components by physical means. Have you eaten mishri, the bigger crystal of sugar? Preparation of mishri involves separation of sugar from homogeneous mixture of sugar and water. Both in our households and in industries, we need to separate mixtures, both homogeneous and heterogeneous, for various purposes. Fortunately, we can recover sugar or salt from its water solution by evaporating the water or even sometimes by heating. To separate different components of a mixture, variety of physical techniques are available. All these separation techniques are based on difference in physical properties of the components present in the mixture. The following two factors decide the best possible technique to be adopted for separation: either type of mixture, the component which you want to collect. Here we shall describe some of the common techniques of separation. 2.9.1 Separation by using separating funnels. The mixture of two immiscible liquids, i.e., the liquids that do not mix, as oil and water, can be separated by using a separating funnel. The mixture is placed in matter in our surroundings. Separating funnel and allowed to stand for some time. When the two layers of liquids are separated, the denser liquid which is in the lower part is first collected by opening the stopcock. See figure 2.12. This method is very useful in industries. Notes. Figure 2.12. Separation of oil and water using separating funnel. The separation of liquid solvent and solid solute from a solution is done by removing the liquid solvent by heating or by solar evaporation. By evaporation, you can recover the solute component only in solid or powder form. If the solvent is inflammable, you cannot use flame for heating. Instead, you can use an electrical heating system in an oil or water bath. You might have heard that salt is obtained from seawater by the process of evaporation in shallow beds near the seashore. 2.9.3 Separation by filtration. Filtration is a better method for separating in heterogeneous mixtures. In filtration, the solid material is collected as a residue on filter paper and the liquid phase is obtained as filtrate. The method of filtration is used on a large scale in industries. Figure 2.13. Matter in our surroundings. Notes. Filter paper. Beaker. Clean water. Stand. Conical funnel. Muddy water. A. Muddy water. Vacuum pump. B. Figure 2.13. Filtration A. Simple filtration. B. Vacuum filtration. 2.9.4 Separation by crystallization. Crystallization is a process of formation of solid crystals from a solution. The method of crystallization for separating solid from liquid begins by evaporating the liquid. Matter in our surroundings. Notes. However, in crystallization, the evaporation is stopped when the solution is concentrated enough. The concentrated solution thus produced is allowed to cool slowly to form crystals which can be separated by filtration. Mishri, sugar crystals, is produced by crystallization from concentrated sugar solution. 2.9.5 Separation by distillation. The method of distillation is used to separate a liquid from a solution of a homogeneous mixture. The distillation is a process in which a liquid or mixture of liquids is boiled in a distillation flask. The vapor is condensed by passing through a water-cooled tube called condenser and collected as liquid called distillate. Figure 2.14. In case of a solution of two miscible liquids, the liquids which can be mixed completely, the separation is based on the fact that the liquids will have different boiling points and there is a wide difference between the boiling points of the two liquids. Rubber cork. Limex condenser. Cold water. Stand. Mixture of two liquid. Thermometer. Distillation flask. Hot water to sink. Tripod stand burner conical flask. Figure 2.14. The 2.9.6 separation based on magnetic properties. How would you separate a mixture of magnetic and non-magnetic substance? In a mixture of magnetic and non-magnetic substances, the magnetic substance can be separated by using a magnet. For example, you will be able to separate granules which are magnetic from non-magnetic substances like sand, sugar, sawdust, etc. Figure 2.15. In industry, this method is used to separate iron materials from non-magnetic materials by using large electromagnets, e.g. of iron ore. Matter in our surroundings. Sugar iron filings. Notes magnet S. N. Iron filings. Iron plus.
Thank you.